you do need to know about different types of analog and digital forms. For example, LPs, cassette tapes, floppy disks, hard disks, CDs, and so on. Now, first of all, we need to know about a digital signal and an analog signal. A digital signal is a coded form of signal that takes the discrete values of 0 or 1 only. It's also known as a binary signal. An analog is not discrete. This is a continuous signal varying between two extreme values in a way that is proportional to the physical mechanism that created the signal. You need to know these two definitions. Okay, an analog signal. We have a cylinder and we have a needle which scratches the inside of this cylinder, the edge of the cylinder. So as the cylinder moves around, the needle scratches along a groove, and as it scratches along the groove, it picks up vibrations. These vibrations are amplified in the diaphragm, and you hear the sound which is trapped in the groove from the funnel. This is an analog signal. So this is what it does. It just moves along the groove and it vibrates, and this vibration is turned into sound, and this is magnified. This is amplified. Here we have an analog signal. You can see it varies from extreme values to 0. This is another analog signal. Right, we need to know about digital to analog conversions. Here we have an analog signal, and it's a continuous range within these. Now, what we have to do to turn it into a digital signal is that every interval of time here, we take the value and give it a value here. For example, this is 7. This one is 8. This one is 9. This one is averaged at 5, and so on. So this is an approximation to the analog signal, and it's written as a lot of as 9 up to a value of 9 here. Then these numbers can be expressed as binary numbers like 7. So 7, for example, can be expressed as it's 1 plus 2 plus 4. So it's basically 0, 1, 1, 1. 8 is 1, 0, 0, 0, and so on. 9 is 1, 0, 0, 1. So we get an approximation to this analog signal with these values here, which are digitized and turned into a binary number. So these can be expressed as ones and zeros. Then what we need to be able to do is to reproduce this sound, and this is the reproduction. So when you get the digital signal, what you have is an approximation to the analog signal, because you have these discrete values here. It's not exactly the analog signal, it's an approximation to it. If you notice, there's one value taken here, one value taken there, one value taken there. So not many values, so this is not a very good approximation to this. What we can do is increase the sampling frequency. In other words, take more samples for unit time. So basically, the higher the sampling rate, the better the approximation to an analog signal. This is a fairly low sampling rate. If we have a higher sampling rate, we can get much closer to the analog signal. So the problems with sampling is that if you look at this is the analog signal, then we take the samples from the signal. These are the samples, and that's digitized into binary numbers. And then if you reproduce or reconstruct the analog signal, it's going to look like this, which is not quite the same as the original. Reproduction is not 100% accurate. Here we have, for example, this value is 1, this value is 4, which is 1, 0, 0. This value is 5, which is 1, 0, 1, and so on. So this is the way it can be represented. Greater the number of bits, the better the resolution as well, which you have more information. And here we have another example here. Original signal, sample taken from the signal. This is the analog signal. These are the samples that are taken. and these are just the samples alone, and you reconstruct the signal, and it's not a true reproduction of this. Now, if you compare this with this, what is the difference? Well, basically, the details are missing because this is not sampled at a high enough frequency. How can this can be corrected? Well, you can have a higher sampling rate. What is the problem with having a higher sampling rate? If you take a higher sampling rate, your device that is recording information is going to have more information. If you take a sample twice as often, the data is going to be twice as much. So you need more space to store this data. Is this important? You basically have to find a compromise between the sampling rate and how much data you want to store. When you listen to music, when you listen to sounds, what is the highest frequency that we can hear? Well, we can hear 20,000 Hertz. So if you have a sampling rate of twice that, then that should be enough for us to be able to pick up any perceivable differences. Is it important to have a higher sampling rate? Well, if you don't have a high sampling rate, these details, these high frequencies here, these small differences here, are not going to be picked up. So basically you lose some of the higher frequencies. So we can hear at around 20,000 Hertz. So if you have too low a sampling rate, you miss some of the high frequency in the original signal. So a good sampling rate would be twice this, 40,000 Hertz, let's say. Well, we don't use cassette tapes so much now. We have a ribbon which is got iron compound which is lined up in a random way. You pass an electromagnet which is connected to an electrical circuit, and this is where the sound comes from. And it makes a pattern in the magnetic field, because when you cause this to have a magnetic field, it will have an effect on the tape. Then later you can play back these shapes in the tape, and the signal is amplified. We can hear a reproduction of the sound that was used to make the patterns in the magnetic field in the first place. Okay, during playback, the patterns on the tape induce a sound similar to the sound that produced them, and this is an analog form. The problem is it's sequential. If you want to get the middle track, you have to fast forward through the tape. There's no random access. An advantage is that they're cheap, they're erasable, you can tape over these, but there's not so much storage capacity, and they're easily damaged. Floppy disks, this is stored in the same way, but it's not stored in an analog way, it's stored digitally. There's a random access, which means it's easy to access any part of the disk. A hard disk is a similar kind of thing. This is used in computers. There is some cobalt in the hard disk, which can be magnetized, and each region on the cobalt disk is a 0 or 1, and you get these split into tracks and into sectors. Each track is split into sectors, and that contains a bunch of information. You have these concentric rings, and you can access any part of this pretty instantly. It just needs to move across, and it will pick up the information that you're looking for.